Okay, and I should be live. So, welcome to the stream, or if you're watching the recording, welcome to the recording, of course. It's raining outside like crazy, so great time to sit down and do a little bit of coding. And if you didn't join for the previous sessions, we already did a lot of work on the Sudoku Solver. But so far we mostly just set up the, the frameworks, and we have the basic solver, which I can actually demonstrate, but the basic solver isn't very, impressive. Just by itself, it can solve a 9x9 Sudoku in 4.2 seconds. And if we apply a little bit of, logic to it, it manages around 0.8 seconds, which, I mean, that's okay. Like, it's not amazing, but it's okay. The slight issue here is that we also want this to solve bigger Sudokus, like 16 by 16, and that's actually what's running right now. And yeah, it's not really suitable for big Sudokus. So the goal for today is actually to do a little bit of a fun stuff, kind of ignoring the next steps that we have written here, and try to implement the human solving techniques for solving Sudokus. If you ever watch someone solving Sudokus online, they might take a long while to solve the Sudoku, but if you kind of count the number of steps that they did, that number tends to be pretty small. And well, computers are great at doing, actions very fast. So just from this, like if we just imitate how humans solve Sudoku, we should actually be able to solve Sudokus very fast, definitely faster than, 4 seconds or 0.8 seconds. And hopefully it will also allow us to solve bigger Sudokus like the 16 by 16 that's still running in the background. And I don't think it will finish eventually, but probably not in any meaningful time. So let's kind of go back to how you actually solve Sudoku. So I have prepared this kind of example here. So this is actually a website cracking the cryptic. This is not my stuff. They have a YouTube channel. I am just using the interface because I think they actually did a pretty good job with the interface, and it's pretty nice. So the basic solving techniques for Sudokus are around basically finding groups of blocks that allow you to then to eliminate options that are not possible. So, I mean, obviously, if I have a 4 here, I cannot have a 4 in this block, in this row, and in this column. So this kind of thing is called a naked single. So if I have a block that has only one option, well, then obviously this is the number that has to be in that square. And this block, this row, and this column cannot have a 4 again. There is kind of an inverse of this rule, where if we have inside of a block only one place to put a number, so let's imagine that we have, let's just use this block here. So let's imagine that we have this kind of situation. So, all the numbers, okay, that's really hard to see. So let me just cut down on the numbers. Okay. This is, of course, nonsense at this point, but let's just bear with me. So let's imagine we had this kind of situation. So in this case, a 6 can only ever go into this space, right? Because none of these other blocks, or sorry, none of these other squares have the 6 as a possibility. So this is kind of the inverse of the, okay, this space has only one possibility and it's this number. This is kind of the number itself has only one possibility to go to. So basically you can kind of deduce that, okay, obviously this has to be a 6 now because that's the only place where 6 can go, and obviously we need to put a 6 somewhere, right? You can kind of generalize these rules though. So let's just look at the bottom two rows that I prepared. So if I have a triple, 2, 3, 4, and this triple spans 3 squares, well, it tells me that if the 2, 3, 4 are the only options for these 3 squares, well then 2, 3, 4 has to be in these 3 squares and it cannot be anywhere else. So what it allows me to do is actually to remove the 2, 3, 4, oops, that's not what I wanted to do. Right. So this allows me to remove the 2, 3, 4 from the other squares, right? And you can slightly generalize this rule. So basically, whenever you take a set of squares within one block, so that can be, a row, it can be a column, it can be, the 3 by 3 block. Whenever you take a set of squares and the number of possibilities within, like possible numbers within those squares is the number of squares that you have, well then obviously those numbers cannot appear anywhere else in the block. So that's kind of the generalized formulation of this rule. So let's just write this down. So if we pick x squares and the number of possibilities within these squares is x, then these possibilities can appear anywhere else in the block. So this is the kind of what we call the naked rule. And if we go back, the inverse again applies. So if you have a situation where over a number of squares, we have some possibilities that only appear in those squares. So in this case, if you look at this row, well, the 2, 3, 4 only appears in these 3 squares. Well, 2, 3, 4 is, 3 different numbers, and they only appear in 3 unique squares, which means they have to be in those squares, and nothing else can be in those squares. So this basically allows us to prune everything else. And you might notice that when I did that, there was already a naked alternative here. So this 1, 5, 6, 7 was also kind of forcing the 2, 3, 4 to be here from the naked variant of this rule. And this is actually what happens all the time. Sudoku is very symmetrical. Like if you think about it, within 9 by 9 Sudoku, we only have to consider sets up to size of 5, up to size of 4, because the symmetrical alternative to the size 4 is size 5. And once we kind of look at the size 4 sets, that inherently forces the size 5s to kind of be solved as well. So that's one of the simplifications. So let's try to write this rule down in something more meaningful. So if x possibilities only appear in x squares, then those squares can't contain any other numbers. So these are kind of the generic rules, and this is what I would like to implement today. We will start probably with just x being 1, and then go from there. The big benefit of these rules is right now we have a backtracking solver. So what the backtracking solver does is basically guesses, and then if it figures out that it guessed wrong, it needs to backtrack. So this kind of requires going back and forward. We need to remember things. For these rules, because these are always correct, if you apply them to a Sudoku where you didn't make any guesses, well, you never have to backtrack, because these can, by themselves, they can never break a puzzle. Of course, if at some point we kind of figure out like, okay, these are actually not enough to solve the puzzle, which can happen, like there are more complicated rules that you can use to kind of figure out more complicated puzzles. But essentially, unless we actually make a guess, we never need to remember anything. We can just keep applying these continuously. If you make a guess, we kind of need to remember the entire puzzle and then come back to it. Because from that point on, we made a guess, and any rules we apply afterwards are kind of suspect because we made a guess and the guess could be wrong. But without guessing, these don't need any backtracking. So let's try to implement these rules. So the solver that we have is here. It's the recursive solver. So we kind of want to do something similar, but let's call it solve smart. And the difference will be that if we actually make a guess, we need to remember the entire Sudoku, because again, we can still run into a situation where we need to make a guess, because again, these might not be strong enough for us to actually solve the Sudoku. So basically here, instead of remembering the square, we need to remember the entire puzzle. Okay. Let me just quickly check if I have. Oh yeah, and if you're interested in the code, it should be, the current version should be up on GitHub and it should be linked in the description. So do I have, I have actually deleted the copy constructors. Oh yes, because the way we set up the blocks, this doesn't work with copy constructors. Okay, so slight change of plans. Let's not do the backtracking solver. Let's not do any backtracking at all. Like, let's say if we cannot solve the puzzle, we will just give up and say, okay, like, this is the best we could have done, and yeah. So what we kind of want to do is we want to start with singles, then go to pairs, triples, and quads. Because they get more complicated computationally. So as long as we can just do cheap stuff, let's just do cheap stuff. And if we run out of cheap stuff to do, then we can kind of, ramp up the difficulty of our solver and go to a higher dimension. But the basic loop, I think, will be something like, while we haven't solved the Sudoku, so while this is false, So while the puzzle is not filled, or is that correct? Well, with this one, we will never run into a situation where check puzzle would return false, because the way we implemented check puzzle is basically, I can go to it. So basically what we do is we check for each block if it has like no colliding numbers essentially. But if we have a situation where one of the squares is not yet set, well, then we just skip it. So this is really just looking for basically incorrect partially solved Sudokus, or if all the squares within a block are set, then obviously it will check if the block is correct as it is. But we do skip over pieces that are not yet set, as in they don't have one single number within them. So this will always return true. We should never basically run into a situation where this returns false. So we basically want to loop until the puzzle is filled, which actually checks whether each square within the puzzle has only one possibility. So while this is not a thing, what we want to do is we want to find blocks that had a change in the previous loop. Because obviously, if nothing changed within a block, there's no reason to apply any logic to the block, because we already did that in the previous loop, right? And for each of the changed blocks, we want to apply the solving logic. And here, here is the space where we kind of want to maybe go first try size 1, or call it x, then x equals 2, and so on. But let's see, we'll kind of see how this works out, if we can make it write this in a reasonable way. There can be definitely a situation where we don't have any change. So if you have a loop where nothing changed and we haven't solved the puzzle, that means that our current solving techniques are not strong enough. So this would basically, in this case, basically want to break out and yeah, just get out of this loop. Right. I think that's kind of the high level logic. So what we are missing right now to make this work is the find blocks that had a change, because we don't really keep that kind of state anywhere. And we of course are missing the actual implementation of the algorithm that will go and apply the solving logic. So first of all, let's do the blocks that had a change. So I think we need to do this. This will touch both the Sudoku and the block checker, I think. Yes. So here we kind of need something like high level that will actually tell us if there was any change at all. And we definitely need like a reset change that will actually go and wipe it. So we want to basically check if there was a change. If there was a change, we want to reset the information whether there was a change, and then apply the solvers. And if the solvers don't change anything, then we bail out. But this thing, okay. So, right, this thing we will need to rely on the blocks themselves. Or actually, we need to keep this information on a square level because it's the squares that are changing. So yes, okay, so that's slightly different. So basically, this line is slightly more complicated. It's okay, so if nothing changed, that stays. Then reset changed. Oh yes, and then find blocks that had a change. So these are three different things. So nothing changed we get from the squares themselves. Reset change, again, that will reset it on top of the squares. But this is basically, we need to go over, this is to be here. We will go over the squares that actually changed and fetch the blocks that correspond to those squares. Yes, yes, okay. So I think then here what I want to have is yeah, basically something like this. I want to have a way to grab the the blocks that had squares that changed. Right. And now we go to the squares themselves. So let's go to Sudoku Square. And basically we need to just keep a flag that will say, hey, like something changed. So it should be fairly straightforward. So we will initialize it to false, of course. Actually, well, if it's a new square, we should initialize it to true because, I mean, on the first loop, you kind of want to go over everything, right? So, yes, yes. Changed. I don't care about the const methods. Right. So this one, I guess we can be slightly smarter. So if data doesn't equal this, then set change to true. If yep, this will kind of be of the same style. Oh, I think I changed my format somehow. Yeah, I didn't really want you to format the Google test. That's annoying. Oh. I guess this should only happen once. Come on. Okay, now we can continue. Right. Oh, debug print should be definitely const. Right. The same here. Then we need the reset that we just set. Right. So now whenever we have a mutating operation on top of a single square, we will remember that the square actually changed. And we only really do it when the, when it actually changed. And then we have this reset. Cool. So now we can go back to our Sudoku. So, well, now this one is pretty simple. So we just go over all the squares. Right? And if we have a square, oh, we are not exposing this at all. That's kind of nifty. We keep computing this stuff, but we never actually return it. So we need the has changed. That just returns changed. Right. So here, if has changed, then we just straight up return true. And if we went over all the squares and none of them have changed, then obviously we return false. Then the reset change is basically the same thing, except we are not returning anything and we are just resetting stuff. So here we will do data ij reset changed, right? And now this is the fancy stuff. So well, optimally we wouldn't return duplicate blocks. So do we actually want to have this as a vector? I'm actually kind of thinking a set would be better. Yes, because we really don't care what's the order we iterate through the blocks. Yes, so a set would be definitely better. Yes, no, of course this is incorrect. Hello, Mr. President. Okay, so changed blocks, right. So we already have a mapping from a square to all the blocks where the square belongs to. That is block mapping, right? So for each square, we have a 2D array of vectors of blocks. So basically, we want this thing again. And we want to have so this is the result. And if the square has changed, what we want to do we want to go over the blocks that this square belongs to, which is block mapping ij. So we just go over that and result insert b. And here we just do return result. Right. So yes, we go over all those changed squares. Looking at this, we actually don't really need the has changed because, well, if we return an empty set, then obviously nothing has changed. Okay, that's not that bad for now. Why is it complaining? Oh, because I didn't make this const. Yes, indeed. Right. So in our main now, so let's just fetch the changed blocks. If the changed blocks are empty, then we just jump out, right? There's the if nothing changed. And we already find the blocks that had a change. Now we can do the reset. So now we can do Sudoku reset change, right? And now what we want to do is for each of the changed blocks, we want to apply the logic. So the thing we are missing right now is actually the implementation of the actual logic. So let's go into that. Right, where do we put that? Do we put it inside of the block checker? I mean, this would kind of make sense because this is kind of the holder of the block. Yeah, okay, let's just let's just put it here. And let's think about this. So the things we want to implement, let me find it, where did I put it down, are these two things. So if we pick x squares and the number of possibilities within these squares is x, then these possibilities can appear anywhere else in the block. Okay. So this is kind of pick n and then do a union of those squares. And if the size of the union is the same as n, then it is this situation. Okay. So we kind of need, yeah, okay, so this would be definitely a recursive thingy. So let's see, how do I do that? So I kind of want this to return the first thing it finds. And what it will return, okay, so I want it to return a vector of positions. Right. Is this a thing? No. Okay. Anyway, so I wanted to find a set, and I think for this, what I want is I want to specify the size of the set. So when I call this with 1, it will find, well, for 1, it will actually find just the elements that are already set, which is kind of useless. For 2, it will find a set of 2 squares that only have 2 numbers in them. And again, I think we kind of want to skip over, actually in general, like if we find a pair, we definitely don't want to make the pair a triple in the next loop, right? Because let's go back to the Sudoku. So if we kind of have a situation, so there's a 3 here, right? And if we would have 2, 4 here, so this is a single and this is a pair, but we can also kind of say that this is a triple, which is very much pointless because it's already covered by the, you know, by these two and this single. Yes. So we would kind of avoid this if we started from like the biggest set and then going down. But it's kind of counter to how humans solve Sudokus, so I'm not super fond of that idea. Um, but okay, let's just ignore this one detail. Um, Actually, let's make it find sets. Let's not make it return the first one because I suspect then it can get potentially stuck. Let's just make it so it returns all the sets of the given size that satisfy this constraint. And it will operate on top of this type. Right. Okay, so for a given size, yes, okay, we need to kind of build this up from the bottom. So let's say I'm already in a situation where okay, slightly differently. So let's say I'm already in a situation where I'm just looking for the last element in however many, came before me. So in this case, basically I'm responsible for emitting this thing. What I need to know is what the union up till until now, which will be okay. And I need to know what's the range of indexes that I can still access. So, okay, if I'm in this situation, so I'm on like last in the row. The only thing I need to do is basically add the last remaining square. So in this case, what I want to do is basically go over I still need this. Okay. So I only go through the range I have permission to access. And what I do is I try union with the previous union and the square I'm looking at right now. And if satisfies something like this, and this would basically check against this thing. Okay. Yeah, I will clean this up a little bit after I kind of write down the idea of the algorithm. So if this condition is satisfied, as in the condition is the size of the union is the same, I guess I can do this. Right. So if size of the union is the same as size, as in the number of elements I'm looking for, then I basically want to do emit, emit set. Right. So this is on the very bottom. So this is the last thing I will be doing if I only have one thing. And I can code this recursively with yes, okay. So I get the squares, I get the size, I can basically get this entire thing again. Okay, and here I basically want to take away one of the squares. So I'll also be looping from first index to size, but it won't be square size because I kind of need to keep space for the element, like the recursive applications. So this will be right. I kind of need something like remaining size remaining. First index minus size remaining minus 1 because yes, so if size remaining is 1, I want this to be 0. And yep, I create okay, it's coming together. Yes, so here basically what I want to have is temporary union, which will be again the same thing as here. And then I basically call recursively myself with the squares again and so on, but size remaining will be size remaining -1, and first index will be I plus 1. Okay, so something like this, and now I need to clean it up and actually make it work. And I also need to actually like have this needs to do something. Right. So I think so actually this should be here as an if, basically. So either we are doing this or that. Right. Okay. So let's clean it up. So we do recursive set find, let's call it. So our first parameter will be the vector of vectors of indexes that we will actually write the results into. Then the second parameter will be the squares that we are working on top of. Right. So this we want to have a const reference. Then the next parameter will be the size we are looking for. So this is the number of elements in the set we are trying to construct. Then the next element will be the running union, let's call it. Which is kind of like the union up to now in the recursion. And then first index equals 0. So when this gets invoked for the first time, we start from index 0. And I guess we kind of need... We need, apart from the first index, we also need the remaining size, as in how many we still need to add into the set. Right. So now, again, we have a for loop. We start from first index. We go until, yes, so this is indeed correct. Now, I guess here we can check. So if so what was it? Yeah, count possible. So if the union already has more things than size, we can just bail out because this is obviously nonsense, right? Because we can never go down by adding things in the union. And actually thinking about it, even if it's equal, right? Because well, okay, so this will depend on what we exactly do when remaining size is 0. But I think equal will be also, like, if we get called and remaining size is not 0, then obviously it cannot be equal either, because we still want to add something. And we will at least add one possibility, like there's no way to add 0 possibilities. Okay, so we loop, and then we will need a new method on the square type. So basically we want to be able to do a union. So this will return Sudoku square t union with another Sudoku square. And right, actually this will be a void because we are unioning into this square. So what we want to do is data equals our data, right? So this is pretty simple. And I guess for this to be complete, let's just add the changed thingy. Not changed equals to, yes, like that. Okay. So this will be our temporary union. So temporary union will be running union with, I guess we can just implement this as an operator, but okay, this is good enough for now. Union with squares I, and because these are pointers, then the reference, right? So we have the temporary union now. So now if size remaining is 1, so this means we are the tail of the recursion. Yes, so if size is 1, now we want to do the check. So if TMP union I'm not sure why this is not completing the code correctly for me. I think I have a typo somewhere. Oh, it's maybe getting confused by this blob of nonsense. Okay, let's just delete it. We don't need it anymore. Okay, so if count possible equals size, then what we want to do is result pushback. Okay, tricky. So here we kind of need to have the information how we got here. So we will need another parameter, std vector size t next to here. So it's kind of related to the running union. I guess we then don't, if we just remember the indexes, how we got here, we don't really need the running union. Yes, okay, so we actually don't need this. And this will be slightly different, right? So this will be the path how we got here. So, okay. So what we want to do here then is Yes, so Sudoku square. Why is this not auto-completing for me? This is weird. I mean, this should be visible. Ah, okay. Okay. So here I actually want to do a weird thing. So here I actually want to yeah. We don't really do like set it to empty because empty here means kind of the opposite thing. So for a Sudoku square, if it's like basically untouched, like all the possibilities are set to 1. So we kind of want, which is what this reset is doing. So so for this thing, we actually want to have a set to empty method that basically does this. Right. Because we'll be unioning inside to this, and we want to start with a 0, so the unions make sense. Yes. So block checker set to empty. Right. And then we go over the path. We go over the path. We do union with squares I, and then at the end we also, because our current guess essentially is not path or part of this, so TMP union, and we actually only ever want to do this if size remaining. I'll call it differently. We only want to do this if size remaining is 1. Right, so here we want to union with our squares, and let's just change it to J because X, because we already have in the outside for loop. And now we want to check it. So if equals size, now we want to actually emit the result, and the result will be so it will be the path, and then push back the current guess, and we want to push this back into the result. Not path, but please. Too many results. Let's just call this R. And yeah, like pushing back into the path, we are pushing back into the local result, right? So if we are at the tail of the recursion, we check whether basically the union of the elements we are currently trying to construct is the same size as the size we are looking for. If yes, then we just emit the result. And if the size remaining is not 1, then we need to do the recursive step, as in we call this with the result, the squares, the size, we create a new path. Size remaining will be size remaining minus 1. And first index will be first index will be I plus 1. Okay. So this should kind of work. Just for debug purposes, I would just try to run this and see if it actually emits the correct things. So right here, trying to think how to debug this or like test it, I mean, rather than debug, but we'll probably, because I kind of doubt it will work on the first attempt. That's usually not how my code works. I guess we can just prepare some examples and try to run it on that. So test this is the test for how did we call it? Recursive set find, right? So let's prepare. Okay, I've already forgotten the crazy interface that I created. Let's just copy paste it here. Okay, so what I want to prepare is the squares. Okay, so I need vector of square type. This would be my data. And I want 9 of them. Right. Of size 9. Yes, and then I can play with these and set them up. So let's start with just setting these very simply. So the first test will be just have everything set to one possible value, and we are trying to find sets of size 1, which should just return us 9 sets of size 1. So we just go over the data, set them all data dot, oh no, data ei dot set to I plus 1, right? So we set every element to I plus 1, and squares first, right? Oh, we still need to the vector of square type pointer, and this one I need to set up. Okay. So we set them to the precise numbers, and then when I call recursive find, recursive set find, with result, yes. So result squares size is 1. Path. Yes, okay, so we can make this interface slightly better by making path an empty path by default. Which means I need to move it here. And I will also deal with the size remaining eventually, because that also should be defaulted. Actually, I wonder, I have never done this. Will this work? Yeah, no, that's doesn't like that. Oh, instead of size remaining, we can have like size consumed, and then we can start with a 0. So it's not a big deal. We can deal with it later. So size remaining will be 1, and we don't need to specify path or first index. So now what we should have in the result is, so first of all, the size should be 9, and expect that, yeah, okay, this is in a different header. Why doesn't it like this? I mean, this file is part of project indeed. It's block checker. Oh, it isn't. How did this happen? Yeah, okay. That was indeed the case. It wasn't part of any project. But come on, reload. It is. Okay. No, don't like Gmod. Okay, let me look this up. It's Gmod expect that I really don't remember what header this comes from. No. Okay, let's look at these files. No. Oh, what? Oh, here is the source files. Okay. Mock sort. No, include gmock matchers. Okay. Like this. I still doesn't like it. Hmm. Okay, I don't want to be spending time on this, so let's just test this manually. That's fine. Oh, I need to export this in the header so I can actually test it. Let's just start with the simple thing. Block checkers, right, run. Redefinition of default argument. Yes, because I specified it in the header. Okay. No matching function. Right, because I changed the ordering of things. So now it's size remaining before new path, right? Indeed. Try again. Okay. Seems like everything is fine. So it does indeed return 9 different things. Damn it, I really want to expect that to work because that allows us to test like whether an array just contains. Yeah, okay, so this just gives me access to gtest, but why? Is it that I didn't specify? Ah, I think this is a problem. Okay, let's see if this works. Okay, stuff happened. So let's see if now I can access gmock. Ah, I can. Perfect. Okay. So now what I can do is to expect that, yes. So result.size, no, result, just straight up. Oh, and now I need a cheat sheet. Container measures. I want elements are okay. I don't really care about the order, even though this will probably be ordered anyway, which is fine. But here what I care about is just that I get a std vector size t with 1 1. Oh, sorry, no, 1 0 1 1 1 2 1 3 1 4. And actually, I'm doing it the wrong way because this is the initializer list setup, so just like this, it should work. 6 7. Oh, come on. 8. So okay, so checking that I have 9 vectors, each of them has one element, and it's elements 0 to 8. Okay, let's see. Okay, I'm missing. Okay, let's just try it like this. This is probably not right. Or maybe it is. Oh, wow, okay. Genuinely surprised that that worked. Okay. Yes. I have 3 tests that are passing. It's kind of annoying that it doesn't actually print out the output. That would actually be kind of useful. I mean, but yes, my tests are passing good. So now we can try something slightly more sophisticated. So let's see. So first of all, let's just reset our data. So what we will do is data I reset. So what reset will do, it will put the square back to the initial state, which is like all the possibilities are present. Right. And let's just create several doubles. Right. So let's just reset first. Okay, that's fine. And now, how do I do this? I mean, I can do it like this, like manually setting the stuff, but that's kind of cumbersome. Should I? This almost makes me think that I should just add a another method that allows me to basically override the value manually, just for this kind of stuff. Yeah, yeah, okay. I think that will be the easiest way, because like doing this programmatically will be so annoying. So let's go to the Sudoku square. So, but let's make this private, because I don't really want to expose this. So let's do override value. And this will just take the backing thing, but let's just make it work with the what's changed. So if data doesn't equal data, then changed is true, and just data equals data, right? And then what I can do here in the test, I first of all need to make the test a friend of my Sudoku square. So the test was named this. Okay. Right. Oh, I'm missing the include for this thing. Okay. Right. And I think I might need to change my do I need to change anything here? Maybe not. Okay, so what I can do then, I don't need this. What I can do is data zero dot override, and I can just go. Is it B? How do we do binary? I've forgotten. In a binary number, C++. Oh, 0B, okay. So 0B, 1, 1. But I need this as okay. Would this work? It's just complaining that it's a private value. I mean, that shouldn't be the case, actually. I just set it as a friend. Okay, this is curious. Oh, namespaces. Oh yes, okay. I've forgotten that that's an issue. Yeah, I need to remove this from an anonymous namespace. That's one annoying part of this, that namespaces for the friends actually matter, so you can do the simple stuff. Okay, so let's set the first two to be a pair, then set the next one to be a single, then the next two to be a pair, So it should be 3 zeros. And then just for the heck of it, let's just do like an interleave pair. So 5, 6, 7, 8. So 5 would be a pair with 7. So I want to add 2 more zeros. And then 6 will be a pair with 8. Okay. So out of this, if I call recursive set find of size 2, size remaining 2, sure. Oh, I'm missing result, right? Now what I expect to get is, this is a pair, so that's 1, 2, 3, and 4. So I expect 4 results. So let's, without even writing the checking for if it matches, let's just try to run this as it is. Okay. And now we actually want to check the content. So we want a 1 and a 0 and a 1 to be a pair. We want 3 and a 4 to be a pair. We want 5 and a 7 to be a pair. And we want 6 and an 8 to be a pair. Okay, let's see. Okay. Just for sanity checking, because I'm getting very suspicious about this test passing all the time, let's just put an error here and let's see if it explodes or not. Yes, okay, so it does, okay, I'm genuinely surprised that I managed to get this right on the first try. Usually doesn't happen. Okay, so we have a thing that gives us the pairs, like finds the pairs, triples, and so on, which is great. So now we can use that. How long have I been online? Let me just quickly check. I will take like a 5-minute pause and I will be right back. My aim for today is really get this into a stage where it actually manages to solve the 16 by 16 Sudoku. So yes, I'll be back in 5 minutes. Okay, and I'm back. So, the set finding routine seems to be working, which is good. The one thing I wanted to change was the remaining size, so we don't have to fiddle with that when we call the routine. So if we kind of invert it, call it consumed. So here it will be consumed, so size minus consumed is 1. And here so this becomes again size minus consumed, but this is size minus size. No, that's fine because these are two different sizes. Okay, this is a little bit uglier, but I guess it cannot really be helped. And then here, I just call it with consumed plus 1 instead of minus 1. Then if I go to the header, here I can just say consume 0. And let's just recheck the logic if it still works. So if I code it with consume 0, this will be size minus 0 minus 1. So if size is, so if size is 1, this is 1 minus 0 minus 1, which is 0. So that makes perfect sense. Okay. Sure, then I can change my test also. So this goes away. And this goes away. And the test should still pass. Yep. Okay, so now we have this routine. So now in the solve, what we do is so we kind of want to loop over block sizes. Right. Actually, size divided by 2, size plus 1 divided by 2, yes, okay. So in a 16 by 16 Sudoku, we want to go up to sets of size 8. And in a 9 by 9, we want to go up to size 4. So it's actually not plus 1. Yes, okay. But this is like this, yes, because we are starting from 1. Okay. So for every block size, actually we don't care about 1 because this just finds basically solved pieces. So we start with 2, actually. Okay, yeah, that makes sense. So starting from 2, we call this thing with the result with the squares. Oops. No, so squares is actually ln, yes. Okay, I'm really thinking that eventually we might want to get all of this, like this we should actually get as a parameter of solve. But for now, let's just do it this way. So result lm, and then size is I, and that's it. So, okay, so if I get, so this is finding the naked sets. So if I find a naked set, what I want to do is for all the other indexes that are not part of the set, I want to remove those numbers from as possibilities, right? So what I want to do is I want to go, well, first of all, what I want to do is create a union. So Sudoku square type, it's, yeah, square type. So square type, so this will be our union. Of size lm, right? What are you complaining about? Ah, obviously. Right. So this is our union. So this is the thing we'll be removing from the other elements. So what we want to do is, oh yeah, so this needs to be in a big loop. X result those size. So we go over all the sets we have found. Yes. Like this. So then within each set, we add the stuff to the union. lm result xy, because this is the index, and I just need to dereference this. So after this, I have the set of numbers I need to remove from all other indexes. So, oof, okay. Yeah, it's kind of an annoying piece of code, but sure, I don't have a better idea to do it. So yeah, I need to go over this time. Actually, like make it J. So now I'm going over my elements. And basically, I want to skip over those that are present in this. So if yeah, okay, so skip over those that are part of the set. And if it's not part of the set, I want to do a minus operation, which I don't have implemented yet. But basically I want to remove, yeah, like this. Okay. So let's go and implement the minus operation. Going back to the Sudoku square, so here I need to implement minus. We get another square. And what we want to do is data will be oh geez. So it should be end equals our data inverted. Is that correct? I think it is. So if I have a 1, 1, 1, 1, and I want to do that minus 0, 0, 1, 1, right? Then the thing inverted is 0, 0, 1, 1, 0, 0. And if I do an AND, I end up with 1, 1, 0, 0, which is exactly the minus. Yes. Okay, this should be correct. And I need to do this crazy check again. So if data is not the same as data and r.data, then it changed. This thing changed. Okay. So we have the minus now. We can go back to here. The minus should work. Okay. Now, so we only want to do this if you are not skipping this thing. Okay. Okay, so this is 50% of our solving approach, right? So we generate all the sets of a given size, and we basically remove the things from the other squares. So if I go back to the main, this is this. If we pick x squares and the number of possibilities within these squares is x, then these possibilities can appear anywhere else in the block. So this is what we are doing now. We still need to implement this. So how do we do this? So here we basically need to count okay, this one is very tricky. What are we actually trying to find? Like we're still trying to find the set, but set of what? We are trying to find a set such that the set size is x, and we have x numbers that only appear in that set and not in the inverse of the set. Okay, that's pretty interesting. Okay, so here, I mean, here we are actually trying to find sets of numbers, not sets of squares, but sets of numbers. And again, we try to find a such set that the size of the set is equals to the size of squares they appear in. So I guess I would have the same kind of set searching logic, but the difference here is that the check I'm doing is for the numbers I have picked. Okay, so let's say we are at the bottom of the recursion to find a set. So we have three, let's say we are searching for triples, right? So we have three numbers. And with these three numbers, what we want to check for is we want to find all squares where any of these numbers appear, and if yes, okay, so and if that number is the same as is basically 3, in this case, if that number if the number of squares is 3, then we have found our set. Okay. So it's kind of the same logic, it's just kind of rotated by 90 degrees, right? Like we, instead of making sets of squares, we are making sets of numbers, and then at the end we are trying to find the squares for those numbers and check what the size of the set of the numbers versus the number of squares is the same. Okay. Okay, that makes sense. Actually, let's copy this and put this here, and let's copy the other thing and put this here where we will put our other recursive thing. So let's just start by copying this entire thing. And let's call it recursive number find. Okay. So the results are still the same, but here we are trying to find the sets of numbers, not sets of squares. Still work on top of squares, that makes sense. The size, still the same, consumed remains the same, path. So path is no longer path. So path is now numbers. Okay. So I think this remains the same. This remains the same. So if we are at the tail of the recursion, so this, okay, so this is where the actual check logic will live. So what we want to do is So this square should contain the numbers that we have picked, and only those. Because then what we can do with that is we can check the other squares. Well, with that we can check all the squares within the block and count how many of them have any intersection, because this is basically where any of those numbers appear. So here we will just have a very simple for loop. I don't have that method on my squares, do I? I don't have like an add possibility thing, right? I just have remove. Okay, so that's easy enough. If I knew how to spell. So adding a number is just ORing with that number. Pretty straightforward. And this is kind of very similar as well. Okay. Right. So here, oops. Yes, I want to do set to empty and then just add the numbers that I'm thinking about. So this will be at x, right? And I still need to I plus 1. Oh, actually x plus 1, right. Right. Because these kind of the loops are based on from 0, but our numbers are based from 1. So now I have a square that has only the possibilities that are part of my set that I just constructed using the recursive approach. And now what I want to do is count the number of squares in this block where this constructed square has any intersection. So for that, I think I will need another new method on my square, which will be basically has intersection and this will be a const thing. So, oh, I've forgotten a reference here, right? So this should return true if data bitwise end with R data is not 0. So if there's no bit intersection on the data, then it doesn't have any intersection. If there is any bit intersecting, that obviously there is an intersection. Right. Which means that now I can count squares, right? Squares size and simply if squares x has intersection with TMP numbers, then count squares plus plus. And if count squares is size, then pushback E, pushback R, yes. So this should work. And does the recursive part change at all? I don't think so. Okay. So let's just test it the same way we tested the previous one. So first index is 0. This is an empty vector. Consume this 0, right. And then you need a new test. Okay, so if we call this on size 1, with a situation where everything is set to 1, it should do exactly the same thing. It should just return us 9 sets where each of them contains one number. Because this is the point where these two rules are symmetrical. Like if basically everything is set, like both these conditions are true, both of these, one possibility only appears in one square. That's true for each of them. And it's also true that if you pick one square and the number of possibilities within these squares is 1, obviously both of those are true. So this should be the same thing. We will need to play with this a bit to kind of get to the same idea. Okay, but before that I need to make this a friend again. Yes. So how do we craft the test for this? Okay, so we are looking for the hidden pairs in this case. So, okay. So this would be a hidden pair because we have the number 1 and 2 only appear in at the indexes 0 and 1, right? Nowhere else. So 1 and 2 should be a hidden pair in here. Then okay, how do we modify the rest so we have more hidden pairs? Okay, so doing this, we kind of destroy the pair at 6 and 8. But now we have a hidden pair of 8, 9 here and here. And I guess this should also trigger as a pair as well, because yeah, okay, so this is both a naked and a hidden pair, which is fine. So what I'm expecting out of this is I'm expecting 0, 1, then 3, 4, yes, 5, 7, no, but 6, 8, no, because these are numbers, so this should be 7, 8. Yes. Okay, let's see. No, okay. Oh, so, well, first of all, this is wrong. This should be a 3. But so it didn't find the 0, 1. It found the 3, 4 and the, wait, 5, 7? 5, 7. Oh, am I calling the wrong thing? Yes. Ah. Let's try again. Oh, cool. So this is failing completely. Now, okay, so it doesn't even work. So, okay, so this is completely broken. So let's have a look at the code again. So if I'm asking for one, size 1, so immediately this thing will go here. With one number, I add that number in here. So numbers will be empty. Okay, so I add the number. Then okay, I need a debugger. So, okay, we are here. So yes, size is 1. Consume this 1. TMP numbers. So TMP numbers, data is 65534. Calculator. I want programmer 65534. Okay, so that's like a completely opposite of what I want. What the heck? How did that happen? I want the exact inverse of this number. What are we doing in... So in set empty, we set it to 0. Okay. Then we set it to 0. Then we go over numbers. Numbers is empty, right? Doesn't really want to tell me, but numbers should be empty. Then we add I plus 1, which is 1. And in add, what we do an... Oh, no. Oh, bad brain, doing stupid things. Yeah. I just want to OR with one bit, not with the inverse of. Ah, stupid. Stop and rerun, yes. Okay. Well, so it at least works for the ones now. Okay. It still doesn't work for the doubles. And it. This is very curious. It doesn't find the 0, 1. Which is weird. Like, why wouldn't it find the 0, 1? Okay, let's have a look at this code again. So this is like two recursions, right? Like I pick 0 here. Then here I just do I plus 1, da, da, da. I push back I. So numbers at this point should have. So I mean, literally, the first time I entered this, that should be the 0, 1 case. So let's do this. Oops, not run, debug. Okay, I need to skip over. Skip over. Yes, so 3, 4, 5, 6, 7, 8. What? Those should have been these cases. Okay, this is getting very curious. What the heck is happening here? Not. Ah, come on. Okay, so now I want to step into. Okay. Size. Okay. Okay. Yes, the size is not 1. Yes, makes sense. I push back the numbers. So now, well, it doesn't show me numbers for whatever reason, which is strange. Wait, what? What the heck is happening here? Is it getting confused because of optimizations? Okay, let's try one run like this. Because I really want to figure out what the heck is happening. Okay, and I hope that now I will get access to more stuff. Oh no, that's. Oh, come on. Ah. Okay, one more time. Right, okay, so now I want to set my breakpoint in here, in here. What? Why did this jump over the breakpoint? Sea Lion, you are being annoying today. Again. What the heck? So okay, these are the 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now I'm here. Why is it stepping in such a weird way? This doesn't make sense to me. Like if I do step over on the constructor of, well, of the thing I don't even see because it's the one of the default parameters, it jumps out? What? Why? Man. So I mean, okay, so now I'm here. Now I'm still here. Sure. Still here. Still here. Still the same thing, 93, still 93, 93, 93. Now I'm here. So now, if I press resume, this should catch on the debug, on the breakpoint here. So let's see. No, it just ends. What? Like, how? What the hell? Now it somehow worked. Wow. Okay. So we have the size 2. Okay. We do the recursive call. Okay, so now we are in the recursive call. So we have size 2, consumed 1, first index is 1. Size minus consumed is 1, so we should step into, yeah, okay, so TMP union, right, set to empty, right, now it should have 7. What? How did it get to 7? Oops. Am I looping over the wrong? No, path is still... Oh, I see my mistake. Oh, I'm such a moron. Okay. This is why you should never copy paste stuff. Of course, I'm calling the old one here. Jeez. It's always something stupid like this. Like, interesting bugs are so rare. It's always something, some really stupid typo that just like is completely obvious. Oh, now it passed. Okay. Amazing. Jeez. Okay, so this actually works correctly. Good. So let's go back to our block checker. And I think we actually want to do the hidden ones first. So again, we don't care about size 1. No, we do care about size 1 because we can have a hidden single that's not yet set. Yes, okay, so for hidden ones, we actually do care about size 1. So this will be another big loop here. So we go from size 1 again to the element size, yes. We do recursive number find. Now, this gives us the numbers that form a hidden set. So what we want to do with that is we want to not do a union, we instead want to do an add of, so you set to empty, yes, add result x, y plus 1. So add the numbers that are part of the hidden set. So now we have the union. Now what we want to do is if we find a square, we don't need to skip, I think. So if we find a square that intersects with our union, then we want to set the value to the intersection. Yes, okay. This is basically saying this is the part of like these numbers. Nothing else can be in this curse but these numbers. So if a square intersects with this union, then we need to remove everything that's not, well, we can also do a minus, right? Yes. No, we cannot do a minus. Oh, geez. Yeah, we want to do the intersection. So if lm has intersection, oops, has intersection with the union, then this element, like this square, should only contain these numbers. So, and I don't think we have, yeah, we basically want to have an intersect, which is a method I don't have yet. Right. Okay. So intersect. I want to implement it in my Sudoku square and remove this intersection. Okay. Void intersect const Sudoku square. If data and our data, then change the construe and data not this. Okay. Right. Okay, so this craziness is done. I would really like to write a test for this. I'm kind of worried to do that. Let's just plug it into the main and see what happens. So we have this solve smart. So we did the change blocks, reset change. We have the change blocks. So now for block.solve, right. And here we just do return puzzle field. Right, so back to the start. While the puzzle isn't filled, we look at the change blocks from the last loop. If nothing changed, we are basically stuck. That means that our solving techniques are not strong enough to solve the Sudoku, so we just pop out with a false. We reset the change flags on all the squares in the Sudoku. So now all the squares will be set that they are not changed. And then we do the solve that actually goes around and changes the squares again. So on the next loop, we will pick up the blocks that were affected by the solve from the previous loop, and we just keep doing this. And at the beginning of the Sudoku, all the squares are set to changed, so this should just work. So let's see if this craziness has any merit. So we just copy this here. So we have the Sudoku system clock. We don't want to do the prune because that happens now internally. Solve smart. And yes, like if we don't solve there, something is wrong. Div count. Yes. Okay. It builds. Okay, I'm really crossing my fingers now. So now it's the slow one. So this is the pure backtracking. That one should take... Oh, sorry. I need to stop this. This will take forever. We need to turn on optimizations again. Right. Reload. And rebuild. Okay, let's try again. So this is the backtracking one. 4 seconds. Didn't solve it. Okay, so in that case, so this could mean two different things. This could mean either we have a bug somewhere, or this could also mean that our current approaches are not strong enough to actually solve the Sudoku that we have as an example. So I'm curious, like it should have mutated the Sudoku definitely. So what we can do is we can do, last time we implemented debug print. So let's just do debug print before we attempt to solve anything, and then debug print just after. Oh, geez. Okay, something is very wrong. Yeah. Okay. We pruned the heck out of this grid. That's. Oh, geez. Okay. Okay, I think I will take a 5 minute break again, and we will try to figure out what the heck is happening, and what the heck is wrong. Why do we delete everything out of the Sudoku puzzle? Um, yep. Okay. See you in 5 minutes. Yeah, okay. So let's try to look into what the heck is happening here, and why are we deleting so many possibilities, because this is definitely weird. Right. So we have tested at least partially our amazing find sets and find numbers functions. So I'm kind of tempted to say those should work. I mean, at least I hope they do. So I kind of wonder. Let's see what happens after like one step of the solver. Um, let's just like after we go through it once, just immediately bail out with a false, which will basically trigger this output. And actually, I want to skip over the two previous solvers because I'm not that interested in waiting for them. Oh, so this happens like immediately. So after one step, this is what we end up with. Okay. Well, that's good to know. Let's have a look at our solve. So the thing is, here I'm doing an intersect. So I'm kind of thinking it's not this part, unless I screwed up the intersect. No, I mean, it's just a simple AND. Intersect should be fine. Um, so this is the actual part that's removing stuff because it's doing the minus. So I'm kind of suspecting that it's that this part is responsible for this mess. Okay, let's just test the theory and comment this out. Well, okay, this looks way better. Um, but now I'm actually wondering if it's not broken in some other way because I don't really see. Okay, let me move this. Oh no, there's some progress. So 5, 6, 7. Ah, okay, so it found a hidden triplet in this column, which makes sense. Did it change anything else? Yeah, I don't really see any other changes, so it only found this one triplet. Which makes sense because there is a there is a quintet in this column, but we don't go up like that high. Actually, let's just see that. Okay, so if I just like rank this up until size -1. Yeah, okay, so now it does way more stuff, right? Um, yeah, basically now it goes for a hidden, what is it, sextet in this row. Yeah, now it does a lot of stuff. It still looks kind of correct to me, although I'm just staring at it, just staring at the numbers, and that's obviously not a good way to test it. But kind of my like the inkling I'm getting is that indeed like this part of the code is correct. Um, so let's investigate what the heck is broken with this. Uh, so I get the results. So these are the indexes of the squares that I have picked. So for each of the sets that I have found, I make a square. Ah, it could have set to empty. Because then we do union with the elements and then we do. Well, that doesn't really explain it. Because then we should skip over everything. What the heck? So this is yeah, the skipping is broken. Because I just realized. Yeah. So the problem I'm seeing is basically if no, that should actually be okay. Because I skip based on the indexes. I go over all the indexes and like this, if this is one of the elements, I skip it. Okay, let's see. Maybe it was just the set to empty that was missing. Oh. So yes, maybe it was just that. Okay, let's see. Let's get rid of this. And let's see if we actually solve it. Okay. So I don't really need to go back to this, but let's just clean up the code a little bit. Okay, and we actually do want to print out the Sudoku, so and actually we want to do the same thing here. And get rid of this, and get rid of this. And just for the heck of it, okay, let's build it. Okay, this didn't really work, unfortunately. But the 9x9 seems to work. Let me just double check if these two are the same. Yes, looks like they are. So, okay, like the time comparisons are ridiculous. Like I completely removed the backtracking one because that one was just mental. But actually, let's just bring it back, right? So, and we can triple check against the basic backtracking algorithm that really shouldn't make any mistakes because it just keeps guessing, and there really isn't anything that could be wrong there at this point. I mean, I can still have some weird bugs in the code, but it's very unlikely that I have any bugs in the code. Okay. So yes, like, I mean, these three written the same thing. So this is the basic backtracking one. This one takes 4 seconds. If we do simple pruning, we get to like 0.8 basically. But this takes like, what is it, 60, 70 milliseconds? Like this is like a, what is it, 100x improvement? Yes. So yes, like this is a big jump in performance. Oh, okay. So for the 16 by 16, it's saying that it couldn't actually solve it, which is curious. Actually, now I wonder. Let's just look at the 16 by 16. I was kind of thinking of like ending the stream for today, but now I'm actually curious. So if I just debug print this Sudoku, oops. How far did it get? And yeah, this would be like a big chunk of text. I mean, okay, this is pretty close to being done. Oh, but somehow this is not good enough to solve this. Which is, I mean, I find this surprising. This would basically mean that this particle 16 by 16 Sudoku is really hard. Or it also could mean that we have some bug in the code, definitely. Let me try one more thing. I really think this shouldn't matter. But let's see, maybe I'm wrong about the complete symmetry of this. So let's just try. It's an easy check, so it doesn't really hurt us. Yeah, it's still not wanting to finish. Okay, so again, either we have a bug in the code somewhere, or seriously, this 16 by 16 is way too complicated to be solved by these basic pruning algorithms, and we need to actually introduce something more fancy, like X wings or Y wings and so on. Problem is, it's really hard for me to judge that based on this. But I mean, if you look at it time-wise, we are in much better shape than last time. Like within 2 seconds, it managed to basically get well, I would call it like a half-solved puzzle. Okay, I think that's good enough for today. So what I think I will do. So if you don't know, I'm streaming Saturday and Sunday, working on this Sudoku solver. So I think what I will do tomorrow is try to grab more examples from the web and try to more like stress test the solving capabilities. And in part, I actually want to get like puzzles that are already solved and basically get an idea of what our solver can do and can't do yet. Yeah. But yes, like, I'm actually surprised at this because, especially for 16 by 16, like from the perspective of the propagation rules, these should actually be simpler because we kind of brute force them more by using big groups. Like in 16 by 16 we go up to a group of size 8, which is not really what a human would do. So either this is like an insanely complicated Sudoku that I managed to grab from the web, or there's a bug, which we will see tomorrow. Okay then. Thanks for watching. If you are watching right now, thanks for staying with me. If you are watching the recording, then thanks for watching the recording. And again, I stream Saturdays and Sundays, starting 2:30 Central European time. Right now it's summertime, so it's Central European summertime. I usually announce that the stream is coming on Reddit and on Discord. So yeah, have a nice remainder of your day, or good night, or whichever applies. And I see you tomorrow, hopefully.